Have you ever wondered if the machines already doing your chores are actually robots? Take the spam filter in your email, or that washing machine rumbling away in your laundry room. Are those robots? Let's look at the spam filter first. It reads your messages and makes decisions completely on its own, sorting out the junk so you don't have to. It is highly autonomous. But we don't call it a robot because it's just software. It doesn't exist out here in the physical world. Now look at the washing machine. It definitely exists in the physical world. It even takes action by spinning your clothes clean. But it fails the test too. It doesn't sense what's happening around it, and it isn't making any independent decisions. It just runs a preset timer. So what makes a true robot? Engineers use a specific 4-part checklist. A robot is an autonomous system that exists in the physical world, can sense its environment, and can take action to achieve a goal. When we strip away the science fiction and look at these 4 practical rules, the mystery disappears. We're left with the exact step-by-step blueprint we need to build a real robot ourselves. Before we start building, it helps to know where the idea started. The actual word robot first appeared a little over 100 years ago in a 1920 Czech play called Rossum's Universal Robots. The author, Karl Čapek, needed a name for his fictional creations. He based it on the Czech and Slovak words for hard work or serf labor. In the play, these machines were imagined as efficient, emotionless artificial humans. Their sole purpose in life was to replace factory workers and perform the hard labor humans no longer wanted to do. That was fiction. The reality arrived decades later, in 1966, with a machine named Shakey. Shakey was the first physical machine capable of analyzing a command, breaking it down, and reasoning out its own path to navigate around a room full of obstacles. The name might have been born from the idea of mindless, repetitive labor, but as Shakey proved, the true test of a robot is its ability to think, adapt, and navigate an unpredictable physical space. To navigate that unpredictable space, a robot needs a body. You can map this anatomy straight to our own. Just as humans use eyes and ears to understand what's happening around us, a robot uses sensors to gather data from the world. The real world is messy. Things move, temperatures drop, and people walk by. If a robot doesn't have sensors measuring those changes, it is essentially driving blind. As the robot collects this data, it builds a state. Think of a state as a total snapshot of everything the robot knows at this exact second, from how close it is to a wall to how much battery power it has left. Sometimes the snapshot is incomplete. If a robot knows where the obstacles are but can't see its own battery level, its state is partially observable. But when it has a clear reading of both its own body and everything in the room, it has a fully observable state. A robot's ability to survive in a chaotic room depends entirely on how accurately its sensors can capture that snapshot. Once the robot knows what is happening, it needs to move. To do this, it uses moving parts, like arms, legs, or wheels. These are powered by mechanical muscles, usually motors, that do the actual work of pushing, pulling, or rolling. Those movements usually have 2 goals. Either the robot is just trying to get from point A to point B, or it's trying to reach out and move an object from one place to another. But you can't just wire a camera directly to a motor. You need a brain in the middle, called a controller. This is typically a small computer chip that takes data from the sensors and sends specific commands down to the mechanical muscles. Building a robot requires solving massive engineering puzzles, from how the frame is balanced to how the motors are powered. But the final bridge is the controller. It has the critical job of linking the robot's senses to its actions so it can function on its own. To make that bridge work, a controller relies on 3 steps: sense, plan, and act. How we organize these steps defines exactly how the robot thinks. One way is reactive control. Here, the data goes straight from sensing to acting with no planning at all. It's like a human reflex. If you touch a hot stove, your muscles yank your hand away instantly to protect you. You don't stop to think about it, you just react. The other extreme is deliberative control. In this loop, the robot senses the world, carefully plans out its future moves, and then finally acts. This is how a robot plays a game of chess. It takes its time to think several steps ahead before moving a piece. Both methods have limits. A purely reactive robot acts instantly, but can't handle complex long-term goals. A purely planning robot is smart, but so slow that the world might change before it finishes its calculations. To build a machine that works in the real world, we have to find a way to combine these two approaches, giving the robot a slow, smart brain for planning and fast, reliable reflexes for survival. This combination is called hybrid control. It links the two systems together, allowing a machine to follow a large-scale plan while keeping its fast reflexes active at the same time. Imagine you've built a robotic waiter. Its goal is to deliver a cup of coffee across a crowded cafe. At first, the robot uses its planning system. It maps the room and chooses the best path to reach the customer's table without hitting any chairs. But halfway there, a person suddenly steps into the aisle. The robot doesn't have time to remap the whole room. Instead, its reactive system takes over, telling the motors to stop instantly to avoid a collision. Finding the right balance between these systems is a skill that takes practice to master. Just like learning a musical instrument, the best way to understand how these parts work together is to start building and programming them yourself. Whether a robot is moving heavy parts in a factory or exploring a distant planet, the core system is the same. It relies on a continuous, autonomous loop, sensing the world, planning the next move, and acting to reach its goal.